This first lesson for Foundation 1 Science, we're going to be introducing the theory relating to the states of matter and introduction of the atomic theory. Now, this is quite an interesting point because the whole concept of atoms goes back quite a long time, 400 BC. If you take that we're now in 2020, 400 BC would be what? 2,420 years ago. That's a hell of a long time ago. All right. So 400 BC, this was the Greek philosopher Democritus. Let me see if my apologies to Democritus. I meant to include a photograph of images of him so that you'd be able to picture what this philosopher looked like. So maybe a little bit of homework for you guys later. Do a Google search on Democritus. Obviously, they didn't have photographs back then, but they did have statues. And so if you Google him, you'll find photographs of statues they made of him, which will give you an idea of what he looked like. Is that relevant? No, not really, but it is quite interesting just to know, put a face to the name. What I can say is that in general, Greek philosophers, they fit a fairly generic mold. They kind of all have beards and they wear robes. Okay. So, atomic theory. Democritus gave us this theory of an atom from the word atomos, meaning not to be cut. So from Democritus, we have the idea that atoms are small, hard particles that are all made of the same material, but they have different shapes and sizes. He suggested that atoms are infinite in number, they're always moving, and they're capable of joining together. Considering how science has developed, his idea was actually beyond genius, because some of the ideas that he came up with 2,420 years ago are completely valid today when we consider the atomic theory of matter and the kinetic theory of matter. We now believe that everything is in fact made of atoms, as he said, and the kinetic theory of matter, the fact that atoms are always moving, that is precisely what is viewed today as well. He started out with this idea that if you take a lump of clay and if you cut it in half, you've now got half your first lump of clay. If you cut that half in half, you would now have quarters. If you cut those quarters in half, you're going to have eighths. And if you cut those in half, you're going to get smaller pieces and smaller pieces. His suggestion was that if you continue cutting things in half, you're going to come down to, excuse me a sec while I get some drawing tools here. You're eventually going to come down to the atom, which is also stated as being the smallest particle of matter. It was interesting, like I said, because for a very long period of time, the majority of scientists did not accept this idea of the atom, and atomic theory was not accepted for a very long time until scientists could establish other ideas that supported it. But going back to Democritus's concept of the atom, he suggested firstly that atoms make up everything. It's a really weak joke, but that's the punchline. I'm not sure if you guys have read this somewhere, science jokes. I'm quite fond of them. So if you guys come across any science jokes, please share them with me. I love to hear them. The joke goes something like this. It says, don't trust atoms. Why? Because they make up everything. It's a stupid pun on making up everything. Okay, so the joke suggests that atoms lie. They don't tell the truth. They make things up. But the reality is that atoms make up everything because atoms are the fundamental building blocks. I'm going to pause for a second just to check my notes here. Lol and cringe. Right, exactly, you guys get it. In my opinion, it's not a good science joke unless it's corny. The best science jokes are exactly like this one. So, now you know what I'm looking for. If you come up with more, please send them through to me. Let's get back to the atomic theory as proposed by Democritus. Atoms are in a constant state of motion, and this relates to the kinetic theory of matter. He suggested that the states of matter depend on the amount of atoms present, as well as the amount of energy with which they're moving. We've later found that that is actually quite correct, because if you take a substance like water, everybody is so familiar with the stuff, and our bodies are made up of the majority of this substance. If you take water and you freeze it, you now get solid water. And if it melts, you've got liquid water. If you boil it, you've got the gas. So the state of the matter depends on the amount of energy with which the atoms are moving. In the solid state, water molecules stick together. They're frozen. They do not move as much. In a gas, you've heated water to boiling point, and now the individual water molecules are free to move with a lot of energy. A unit of power. Oh, right. What? Very good. I like it. Okay, back to the topic at hand. We're speaking about the energy with which particles are moving. So in a gas, particles move with a lot more energy than they do in a solid. The next point, Democritus suggests that an explanation for the fact that different materials have different properties can be found in the idea that these atoms have different properties themselves. So in a metal, atoms are able to hook together, forming a strong solid, while in a liquid like water, the atoms are smooth and round, so they do not cling to each other, suggesting that water flows. We've since found that there is a little bit more technical detail to this, but in effect, Democritus was right. 2,420 years ago, long before the invention of microscopes or any of the scientific apparatus we use today, he actually understood the true nature of matter. What we speak about now are forces of attraction and intermolecular forces of attraction responsible for the type of bonding that takes place between atoms. And we've been able to come to that theory based on the concept of electrons and protons and atomic structure. He didn't really go into detail about the nature of the atom, but he understood that there had to be this idea of the atom and that different materials have got different physical properties. Water is very different to iron. Water is soft, it flows. Iron is hard, it's solid, it doesn't change shape. So the atoms making up iron must stick together in ways that the atoms in water do not. We now, like I say, understand this in terms of intermolecular forces of attraction. But considering what he had to work with, it's really impressive that he was able to understand this concept. So Aristotle, Plato, earth, fire, air, and water. Aristotle and Plato came after Democritus. They discredited his view and they said, Democritus, what have you been sniffing? You're just mad. How can anyone believe in this ridiculous idea that everything's made up of atoms? You can't even see atoms. Your theory's nuts. The common view for over 2,000 years, guys, that's a long time for an idea to hold weight. The common view was that everything is made up of fundamental elements, 5 elements. We've mentioned 4 of them here already. Earth, water, fire, and air. They suggest that if you look at everything around you, what's visible to the human eye, we can understand that everything is made up of these four elements, and combinations of these four elements can give rise to the fifth element. I'm not sure if any of you guys saw that movie some time ago with Jova Brovovich, what's her name? Anyway, the fifth element, great sci-fi movie. The fifth element can be considered as things like wood, iron, and in a more esoteric sense, life itself. Consider your body. I assume that if you're tracking this lesson, you must be alive. You're alive, you have a body, right? Where did your body come from? Well, your body is made up of the elements that you find around you. You eat food, right? If you don't eat food, you die. So your body is made up of food. Where did that food come from? We eat plants, we eat animals. Where do the animals come from? The animals eat plants or they eat other animals, okay? The common denominator then is that they eat plants. Where do plants come from? Plants come from the earth. Do they just grow out of the earth? No. Plants need water, plants need air, and plants need fire. They need heat from the sun. So you take wood, for example, a tree, or a plant that you could eat, mealies, tomatoes, whatever, okay? That is a product of these four elements. And so everything else that we look at, iron. To get iron, you need to first mine the rock, so earth, and then to extract the iron from the rock, you need fire. You also need air for the fire, and you need water for the chemical processes. So iron is a construct from the four basic elements. So the view of Aristotle, Plato, and many philosophers after them, for approximately 2,000 years, was that everything around us is made up of these four elements, and those four elements can be combined to give you the fifth element, life. Your nature of being alive is based on a combination of those four elements. Yes. Note, increase in temperature also increases the pressure. In order to understand that, we have to think back to the kinetic theory of matter. We've seen how increasing the temperature increases the kinetic energy of the particles. With more energy, you get more movement. So you increase the temperature, you increase the kinetic energy. You increase the kinetic energy, the particles are moving around with more energy. It's striking the walls of the container harder and faster. So, increase in temperature increases pressure, since with an increase in temperature, there is an increase in the kinetic energy of the gas particles. They now move faster and with more energy, and therefore strike the walls harder and more often. This increases the force they exert on the walls of the container, and therefore the pressure increases. Let's think about a few other factors in terms of temperature, pressure, volume. If we increase the volume, we decrease the pressure. And again, for the reasons that we've just discussed. When you increase the volume, you increase the space in which the particles can move. The particles have now got more space to move around in, and therefore there will be fewer collisions per second with the walls of the container. If there are fewer collisions per second, it means that overall there is a reduced force being exerted on the walls of the container, and we would measure that or detect it as a reduction in the pressure. So if you want to increase the pressure, increase the temperature. If you want to decrease the pressure, you increase the volume. Let's have a look at the next 2 points. If we decrease the volume, we increase the pressure. As we mentioned in the previous point, but in reverse. If there's less space to move in, the gas particles collide more often with the container. That increases the force exerted, and so the pressure increases. Lastly, if we increase the number of gas particles, we increase the pressure. So, what we can say in conclusion is that pressure is inversely proportional to volume. If you decrease the volume, you increase the pressure. And vice versa. If you increase the pressure on a gas, you're squashing it into a smaller space, you decrease the volume. When we talk about volume and pressure, I find that the easiest way to think about it is in terms of water. We've all probably had experience of swimming, and you'll have noticed that the deeper you go in a swimming pool or in a dam, for example, the deeper you go, the greater the pressure you feel on your ears. That's because as you go down below the surface, the amount of water above you pressing down increases. This graphic that I found is quite interesting because what it shows us, roughly speaking, is the relationship between depth, pressure, and gas volume. So on the surface, you're at atmospheric pressure, 1 times atmospheric pressure. As you start to go below the surface, you've now got atmospheric pressure pushing down on you and a pressure due to the mass of water above you. So if you go down 10 meters, you've now got an effective pressure of 2 times the atmospheric pressure pushing down on you. And a volume of gas will have shrunk from 100% on the surface to 56%. Then go down to 20 meters, pressure pushing on you is 3 times atmospheric pressure. The volume of gas that would have been maximum at the surface has now shrunk to 1/3 of its original volume, and so on as you sink deeper. If you get down to 50 meters, you are now very deep under the water. Effectively, you have a pressure of 6 times atmospheric pressure on top of you, and the volume of air that you take down has shrunk to 17%. So a large volume on the surface is compacted into a small volume down at 50 meters. Just as a matter of interest, I want to give you this. 50 meters divided by 2.7. That's approximately 18 stories below the surface of the water, because 1 story is approximately 2.7 meters. Okay, so moving on. In water, the greater the depth, the greater the pressure. We notice this because water is denser. The feeling of pressure is more noticeable when we're swimming. We don't really feel atmospheric pressure on top of us because it's there all the time. We're not really aware of it. Also, air is much less dense than water. So with our normal sensitivity, we don't pick up much in terms of shifts in atmospheric pressure. To do that, we need to build special equipment, specifically an instrument called a barometer. A barometer reads barometric pressure. Barometric pressure, also known as atmospheric pressure. The human system is not sensitive enough for us to register changes in atmospheric pressure, but a barometer can pick up these changes. And that can be quite useful for geographers and also people who are monitoring the weather, because shifts in atmospheric pressure indicate changes in the weather. I'm not sure if you guys were aware of this, but if atmospheric pressure drops, that means a storm is coming. If atmospheric pressure rises, generally speaking, that means that you're going to be having sunny weather, clear skies. So by measuring atmospheric pressure, you're able to predict what the weather is going to be like for a period of time. Moving on, just looking at this graphic, illustrating a little bit of information about atmospheric pressure. At high altitudes, up in the thermosphere, we're looking at approximately 10 kilometers above the surface of the planet. We find maximum volume of air, and that corresponds to the surface of the water. At surface level, the atmosphere has its greatest volume. But if we were to now go up 10 kilometers, we would find that this volume of air expands yet again, because the higher you go, the less pressure pushing down on you and the increase in volume. So at atmospheric level, volume of air would be very small, and the higher you go, that volume of air expands until you get to the upper level of the atmosphere, where you've now got zero atmospheric pressure. That's right on the edge of space. That's where our atmosphere starts to end and outer space starts to begin. So, the atmospheric pressure we experience down at ground level is effectively due to this column of air, 10 kilometers of air above us. In a similar way, if you're underwater, you experience pressure due to a column of water pressing down on you. But because water is so much denser than air, notice here we get 6 times the atmospheric pressure just by going down 50 meters, as opposed to 10 kilometers of air. That's 10,000 meters to give us the equivalent of 1 times atmospheric pressure. Here's another slide I've prepared for us to look at, giving a little bit more in terms of the relationship between the height of the column of air and the pressure that it exerts on us. But again, the basic point is that with increased altitude, you get a decrease in atmospheric pressure. The last point I want to introduce for this lesson is just a little talk about the diffusion of gases. When we started, we spoke about how the kinetic theory of matter accounts for the movement of particles. That movement of particles then accounts for the phenomenon that we can measure, and that is pressure. We can measure gas pressure as a direct result of the movement of individual particles. The movement of particles of gas can have another effect which is of interest to us, and that is the diffusion of gases. From the kinetic theory of matter, we know that all matter is in a state of constant motion, and this means that in a container, gas particles will randomly move about until they're eventually evenly spread throughout the container. And that's what this graphic shows. Initially, you introduce some gas into a container. If you seal the container and leave it, over a period of time, these individual particles, because they're all moving around the whole time at random, they eventually distribute themselves so that they evenly distribute throughout the volume of the container. We give a technical definition of diffusion. We would say that diffusion is a net movement of atoms or molecules from a high concentrated region to a low concentrated region. And that's what we're seeing here. Where the gas molecules are all close together, we have a high concentration. And here, where they've now spread out throughout the entire container, that's a low concentration. In other words, the movement of atoms or molecules is from a high chemical potential to a low chemical potential. And this can cause a mixing of gases to take place spontaneously in a container. If you had more than one gas here, each gas will move around at random and diffuse until it occupies the entire volume of the container. That would result in a mixing and a spreading of the individual gases. Diffusion also explains how the smell of a substance can carry across a room. I'm sure you guys must have noticed at home, if someone's baking cookies or a cake in the kitchen, you can often smell freshly baked cake and cookies anywhere in the house. After a little while, the smell of that baked cake diffuses throughout the kitchen and starts getting into other parts of the house. And so you can detect.